This is our UCF EMBS Group 4 mSheep EMBS statewide competition submission for Human Health Monitoring and Diagnostic Device Challenge.
So our prototype aims to assist in the diagnosis of monitoring a sleep deprivation state known as microsleep. Sleep deprivation is a well-known health condition. For our prototype to work, we would need a driver who, while driving, is starting to show symptoms of sleep deprivation. The sleep-deprived individual would experience a symptom of sleep deprivation called fatigue, which induces microsleep. Microsleep is a brief period of sleep lasting around 30 seconds. Annually, microsleep causes 600 deaths and around 50,000 injuries. Our prototype aims to detect a sleep-deprived individual's increased blinking rate, which is a researched indicator of sleep deprivation. And in doing so, our prototype would be able to detect microsleep. And due to detecting the symptom of sleep deprivation, we would detect sleep deprivation. We would be able to detect that moments before some kind of fatal injury or fatal death occurred. So that's how we aim to prevent the bad scenario. Our target user population would be really any kind of individual globally who has access to electronics, whether that be through Amazon, DigiKey, or some kind of other online retailer, or a physical online in-person distributor. Our target this prototype could also be marketed to, for example, long-haul trucking services, where they could employ these devices across their fleet to prevent commercial vehicle deaths or injuries or fatal accidents. We really wanted to have a solution that was modular in our product choice. So we specifically chose commercial off-the-shelf devices that were still being manufactured and are still commonly and easily accessible. In the event that some of our components did become obsolete, our design supports switching out components modularly. So as technology advances and as certain parts become unreachable and inaccessible, the individual or a new product would come out that would just switch out those obsolete components. The importance and relevance of the problem is that this is an issue causing around 2 deaths per day from that 600 death per year figure. So our prototype would be able to save lives.
Existing technologies or solutions for fatigue tracking in use for long-term drives include commercial anti-sleep gadgets, but they rely on motion sensors to detect the forward nodding motion for drowsiness indication. However, that can be inaccurate and not based on physiological symptoms. And additionally, some vehicles include fatigue tracking. However, buying a whole vehicle that has that capability can be expensive and not modular. There's also vision-based camera monitoring using per close for how often or how long your eyes are closed for, but it's limited by the quality of the video feed. So with our EOG solution, it's using a physiological symptom to detect the drowsiness, and the rapid eye blinking will allow us to detect the drowsiness before you're beginning to nod your head or it's too late. So an earlier detection. On the right, we have our bill of materials, which you can see that the whole system ends up being around $34. So it's much more reasonable than existing gadgets.
Our device overview slide consists of a teammate's placement of the surface electrodes, the entire hardware prototype breadboard towards the middle, and the main computing task of the Raspberry Pi Pico, the microprocessor, on the bottom right. Starting from the left, you can see towards the back of the teammate's right ear is the reference electrode placed. Towards the bottom of the right eye is the positive in electrode, and on top of the right eye is the negative in electrode. The way our device works and our prototype works is that looking towards the middle of the screen, you can see towards the left of the breadboard, we have the three aforementioned electrode connections going into our EEG sensor. Our EEG sensor then interfaces with the Raspberry Pi Pico via its ADC, ground, and 3.3 volt pins. And then the Raspberry Pi Pico interfaces with our remote patient monitoring solution. Just a quick rundown of that remote patient monitoring solution. It consists currently of a laptop that's running a visualization program. And really what we wanted to achieve with that remote patient monitoring solution is for it to, once a micro sleep or fatigued driver state is detected, for an audible alarm to be deployed for the driver to hear, and that would indicate to the driver that they are fatigued, and given proper instructions, maybe from like a instruction manual that we would provide, they would know to halt their driving and pull over, or find a safe place ahead of the road to stop driving. So the Pico interfaces with the EEG sensor and also the remote patient monitoring solution. Going down to the transfer function, this our prototype has the ability to be more accurate. If you see towards the first equation listed in the transfer function image, if you see the n factor, that can be increased given the amount of channels you're using. So the n is the number of bits of the channel. Since we're only using one channel, that's a fixed rate. But if we were to use more EEG sensors, we would open the door to more bits to be able to travel per channel. And that would increase our accuracy in sensing.
The software is divided into two main components that work together as a real-time drowsiness detection system. On the Raspberry Pi Pico side, the embedded code continuously samples the analog EOG signal, converts the ADC readings into microvolt values, and performs simple threshold-based blink detection to identify significant eye activity events. On the computer side, the Flash-based software receives the streamed signal data over the serial, applies additional signal processing and filtering, tracks blink activity over a rolling time window, and classifies the driver's state as alert or drowsy. It then sends this process information to the dashboard for live visualization, allowing both signal monitoring and fatigue state feedback in real time. With the data flow, it begins at the electrodes, which are placed behind the ear, the negative above the eye socket and the positive below the eye socket, to measure the difference in electrical potential. This is then captures the user's eye-related bioelectrical activity. That weak analog signal is passed into the Bitolino amplifier, where it's amplified and conditioned for measurement. The Pico then samples the amplified signals through ADC and converts it to digital values, streaming it over the USB serial to the laptop. On the laptop, the software performs filtering, blink analysis, and drowsiness classification, which is visualized through the dashboard in real time for alert monitoring.
So our hardware connections consist of the EEG sensor shown on the right figure and the Raspberry Pi Pico. You can see the various jumper cable connections that we had from the breadboard illustrated here in electronic design automation software KiCad. On the bottom, the left side of the EEG sensor is what connects to our reference electrode, our in positive and negative electrodes, and then the right side connect to the Pico to transmit the respective electrical signals measured and to power on the sensor using a 3.3 volt connection from the Pico. The top of the Pico is shown to depict a micro USB to B connection port. This is what we're currently connecting to a laptop to be able to connect or interface the Raspberry Pi Pico with our Flask UI, which is acting as our patient monitoring solution. We would have liked to have the patient monitoring solution be kind of like a all-in-one package that would be able to be downloaded or accessible on the patient's end device, whether that be a laptop or a phone. And we would want our proposed software all-in-one solution would make the sleep deprivation and microsleep metrics measured available on that software package. And then that would be viewable not only to the patient, the actual driver, but also the any loved one who might be tuning into to that software application via a mobile network or just a network in general. Um, and yeah, so on the left, the top left of the diagram, you can see um, our breakdown of our hardware components, the respective current draw voltage and wattage calculations. And using that and using a proposed LiPo 3.7 volt 500 milliamp rechargeable battery, we would have a predicted battery life of around 18 hours, 7.9 hours. If the battery is able to only receive around 80% full charge, which is kind of common for these LiPo batteries, our system would be able to support around 15 or 14.3 hours of operating use.
For our live demonstration, we used our software and the hardware combination in a driving setting. Of course, the user is not currently driving, as that would be dangerous, but as you can see, when the user is blinking their eye rapidly, perhaps they've been driving for many hours and they're a bit fatigued. The dashboard shows the peaks in the filtered EOG signal chart for every time they blink, and the software is computing the rate of the blinking, which ultimately alerts the user through the alert versus drowsy UI.
Yeah, so this product really worked as we expected. We didn't have to tinker too much with the actual demonstration. We were thankful enough to have a good enough design before we tested in the testing environment, which is the vehicle, to not have to iterate too much. So yeah, this is our live demonstration. And as Queenly said, you have the alert status and the filtered EOG, the raw EOG, and the eye closure activity graphs displayed there. In our to-market product or our finalized product, we'd likely have other metrics that would be able to be accessible on the patient monitoring solution. But for now, these 4 statuses are what our patient monitoring solution supports.
For our team reflection, when we were working with the hardware and the software, we noticed some difficulty with using the EEG amplification and getting the right signals, as well as the right placement of the electrodes. We also noticed that you can get electrical noise from anywhere, and specifically like dimming the light sources helped with the signal retrieval. In addition, there was a part where the component needed a solder fix for the amplification module, so we had to fix that as well. For the software, it was typical mix of debugging and troubleshooting, but using the Flask application was easy to launch, especially in like a non-Wi-Fi enabled environment like a car. For future improvements or scalability, we want to implement the Bluetooth connection for the EOG signals to the UI, as well as have it be able to connect to the network, because then, as we mentioned earlier, it can help other people realize that maybe you are in a sleep deprived state and they could intervene. For accessibility, our BOM came out to $34, which is pretty moderate for using physiological signals to derive your fatigue state. And to obtain the system with these like currently available components that you can purchase yourself, it's pretty easy to put together as like even if you have no experience.
Yes, yeah. As Quinley said, um, if even if someone were to be breadboarding our prototype, they would have a really easy time. And yeah, our to-market product would of course be encased in some kind of polished, finished to production enclosure. And the end user wouldn't have to fiddle around too much with the components. They would just have to correctly apply the electrodes in whatever distraction-free manner we decide to have them placed. Of course, this is just a prototype, so we really just wanted to show off the capability of what our system could do. And yeah, we had a really fun time doing this. Some of the challenges we faced, like Quinley said, we think that maybe with the soldering, that maybe some of the solder made continuity with, or two pins made continuity with each other via some of the solder. But we got that working. And yeah, really minimizing electrical noise was critical in testing our solution initially to really refine the software. And yeah, we had a great time doing this. And
yeah, it was really fun to work with the power requirements of each component and figuring out whether it's a software or hardware issue, and kind of changing our environment settings to best fit the signal obtained. And finally, we developed the product mSheep. We're happy we're able to develop our device, the mSheep.
the micro sheep detects micro sleep, and it was a great time working on it.